exceptions to the octet rule, because if there's a rule, there has to be an exception, right? So there's a couple of different things, different reasons that molecules can violate the octet rule. And one is if there's an odd number of electrons. So there are things called free radicals. These are molecules and ions that have odd numbers of electrons. And if you have an odd number of electrons, it is just not possible for all the atoms to have an octet. It's just not possible. And so these tend to be stable and unstable and very reactive. And you've probably heard of free radicals and maybe the idea that you should consume lots of antioxidants to mitigate the effect of the free radicals. But what free radicals are molecules or ions with an odd number of electrons. They aren't happy. That's why they're unstable and reactive. They are looking to get another electron or to lose an electron, and so they will react in order to do that. So we're going to draw the Lewis structure for no. Isn't that what that is? Shouting, right? All caps. So that's no. It's one of my favorite molecules. So here's no. How many valence electrons total in no? 11, right? So 2, 4, 6, 8, 10, 11. Well, we need to share a little bit more. So let's take these two guys and put them in here. Nitrogen's happy now. Is oxygen happy? No. Is there anything we can do to make oxygen happy? The only way we can make oxygen happy is to make nitrogen unhappy, right? So, but why would we want to do that, right? So, Lewis structure, Lewis model says this isn't good. Like it says up there, the Lewis model can't handle everything. So what do? Well, you just write the best Lewis structure that you can, and then put the odd electron to minimize the formal charges. There's another possibility here. We could do a triple bond, right? So that's 2, 4, 6, 8, 10, 11. We could do that. Now oxygen has an extra electron. So let's look at the formal charges. Formal charges are the most straightforward way of deciding which one of these is best. So on this nitrogen, what's the formal charge? -1. Nitrogen brings 5 to the molecule, but in this arrangement, he's owning 6. 5 minus 6, -1. Basically, he has more electrons than he came with. And here the oxygen brought in 6, and it's got 1, 2, 3, 4, 5. So the oxygen has a +1. So that's not good. Oxygen's more electronegative. It should have the negative formal charge. Well, let's look at this one. How about this nitrogen? What's its formal charge? 1, 2, 3, 4, 5. It's got a formal charge of 0, right? Yeah. And the oxygen? 0. Oh, we may have found a winner there. Let's look at this guy down here. How about this oxygen? 0. 1, 2, 3, 4, 5, 6, and 0. So we have a tie. A tie with zeros. How would we choose between those? Because I'm actually just kind of wondering it myself right now. What do you think?
Would the triple bond be stronger?
A triple bond is stronger. I'm also thinking, see, that oxygen has 9 electrons, right, instead of 8. And in the other structure, the nitrogen has 2, 4, 6, 7. And so is it better to be one short or to have one extra? I think it would be better to be one short. But off the top of my head, I can't really give you a good reason for that.
We'll write the extra electron out. You can't get labeled as 8.
Right, because that is the problem. And when we look farther into what the electrons are doing and the hybrid orbitals and stuff like that, I think it's better to have, at least, certainly with these elements are in period 3. They're small. They don't have any d orbitals that they can expand out into. And so for these guys, we should definitely choose the one where we have too few electrons on one, less than 8 rather than more. So we're going to choose that guy. Another way that the octet rule gets violated is by an incomplete octet. So boron tends to form compounds in which it has 6 electrons. If you find boron on the periodic table, he's one of the smallest ones, right? He's number 5. He's not up there with hydrogen and helium, who violate like every rule there is, but still he's one of those little guys, and so he doesn't always follow the rules. So we find that boron often forms compounds in which it has 6 electrons. So let's look at BF3. So BF3, probably reasonable to put the boron in the middle, right? And put the fluorines around the sides. Yeah, I should have started lower. Boron, fluorine, fluorine, fluorine. Each fluorine has 7 valence electrons, so 7 times 3 is 21. And boron has 3, right? So 21 and 3 is 24. So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now normally, what would we do? We would take a lone pair here and make a double bond. Well, let's do that down here. And then how would we decide between these two? What did we just learn how to calculate? Formal charges, right? So this fluorine, what's its formal charge? 0, right? So that one's 0. How about this one? Same arrangement, right? 3 lone pairs and half a bond. So all those guys are 0. What about the boron? 0. Okay, let's look down here. We can predict that this fluorine and this fluorine are 0. What about the boron? Plus 1 or minus 1? Minus 1. It brought 3, it owns 4. 3 minus 4, minus 1. And that fluorine? Without even counting, you can predict that it's plus 1 because they have to add up to 0. The fluorine brought 7, and it only gets 6 in here. So 7 minus 6 is plus 1. So why not this structure? Because that doesn't have the lowest formal charges. When we do it this way, everyone has 0 formal charges. So boron tends to do that. Beryllium also tends to do this. So, he's right down there, one smaller than beryllium, than boron. And then beryllium's kind of funny because beryllium's a metal, right? What's he doing with octets? But he will lose electrons, and sometimes also he will share but we're going to like kind of ignore that part. So we had odd numbers of electrons, we had incomplete octets, and then we can also have expanded octets. So when we get to elements in period 3 and above, they can expand their octets from 8 up to 12 or even 14 electrons. I'm saying draw the Lewis structures for those two molecules, and yet I gave myself essentially no room to do that. That was smart thinking. Well, let's try it anyway. AsF5. I'll try to draw small. Blue was maybe not the best choice of color. How many valence electrons does arsenic have? 5. And the sulfurs, the fluorines have 7. Oh, the dots are too big. I don't feel like making them smaller. They're all going to run into each other. You get the idea, right? What are the formal charges on the atoms in there? They're all 0. They are all 0. Because fluorine brought 7, and in all of these, it's got 6 in lone pairs and 1 from the bond. Arsenic brought 5, and it's got half of 5 bonds, and so it also has a formal charge of 0. Let's do a different color and make the dots a little smaller. The other one is SF6. SF2, 3, 4, 5, 6. I don't know what I was counting. Those are not smaller enough. What are the formal charges on these atoms? They're all 0s. These are both stable compounds. Arsenic pentafluoride and sulfur hexafluoride. Sulfur is in period 3. Its valence electrons are in the 3s and 3p orbitals. What it can do to form 6 bonds is it can expand into the 3d orbitals. Nitrogen and oxygen can't do that because they have the 2s principal energy level. There's 2s and there's 2p, and there is no 2d. And so they cannot expand. But arsenic's in period 4, and so it can expand into the 4d orbitals. So let's look at sulfuric acid, and I'm going to go to a different page so that we can have some space. So let's look at sulfuric acid. So let's see here. S, and there's O, and O, and O, and O, and the H's are going to be on the O's. And we're not going to talk about Y necessarily. Oh, I made that really, really big. How many valence electrons do we have here? We have 4 oxygens. They each have 6, and sulfur has 6. So that's 5 things with 6. That's 30, and the hydrogen's 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, oh, 32, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Okay, so that looks good, right? Octet rule. Nice. Well, let's do another one. I'm going to change color because these are going to run into each other because I drew the first one too big. Dang it. Okay. What if we did something like this? Two, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. That doesn't look like it would be the best Lewis structure, does it? The oxygens and hydrogens are all good with their octets and duets, but sulfur has how many electrons there? 2, 4, 6, 8, 10, 12, right? It doesn't have an octet, it's got 12. It doesn't have 8, it's got 12 in its bonds. Let's look at formal charges. We'll make formal charges, I don't know, red this time. So this oxygen, what's its formal charge? It brought 6, it has 7. Remember, when we're counting formal charges, we're going to count half this bond. So it's 1 plus all the lone pairs. It's got 7, so it's minus 1. And this guy up here is also going to be minus 1, isn't he? How about this oxygen? That one's 0, and this other oxygen is 0. What about the sulfur? Plus 2. So, not so great, right? Let's look over here. How about this oxygen? 0. And this one? 0. And this one? 0. And this guy down here, 0. And how about the sulfur in the middle? Huh. That's better, huh? It's better. Any questions? So what we see happen is that octets get expanded to lower formal charges. That's how we think about it. The period 2 elements never have expanded octets. Periods 3, 4, and above, sometimes not. So let's write a Lewis structure for xenon tetrafluoride. It's one of those rare noble gas molecules. So we have xenon in here, and fluorine, and we'll just put the fluorines around the outside. I don't like that. I'm going to start over here, right, a little more space. Xenon. Fluorine, 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 fluorine. Okay, 4 fluorines, they each have 7. 4 times 7 is 28, right? And xenon has 8. So 28 and 8 is 36, right? So we've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We've got 4 more electrons. Where are we going to put them? We're going to put them on xenon. Xenon's a big boy. He can handle it. He has an expanded octet. And if we look at formal charges, fluorine When fluorine has one bond and 3 lone pairs, fluorine has a 0 formal charge. So all those are zeros. What about xenon? 0. Okay, let's do phosphoric acid. And so there's 3 hydrogens. They hang off the oxygens. Okay, so I should really write this out. 4 oxygens, they each have 6 valence electrons, and we've got 3 hydrogens, so that's 3 electrons, and phosphorus is 5. So that's 8 plus 24, that's 32. Did I do that right? That's one of those things on an exam. Yes, you can do math like that in your head. Check it on your calculator. 2, 4, 6, 8, 10, 12, 14, okay, 16, 18, 20, 22, 24, 26, 28, 30, 32. That looks like it'd be good, right? In Chem 3A, we'd say, yay, you did it. And then we lied to them. Let's look at the formal charges. Well, what's the formal charge on this oxygen? 0. When oxygen has two bonds and 2 lone pairs, it has a formal charge of 0. Oxygen tends to form 2 bonds and have 2 lone pairs. So this guy's 0, this guy's 0, that guy's 0. What about this one up here? It's -1. Because it brought 6, but now it's got 7. And what about the phosphorus? +1. So that's where we say, well, what if we expand an octet, could we get those down? What are we trying to do here? We're trying to take some electrons away from oxygen with its negative and give it to phosphorus. So let's get rid of these because those are going to change. The rest of it's going to stay the same. Let's take a lone pair from oxygen and make a double bond with the phosphorus. So now what's the formal charge on this oxygen? 0. And on the phosphorus? 0. So that's better. Isn't that cool? So formal charges are just something we made up, but we made them up because they're really useful. Okay? Really useful.